Welcome to ITEDST IS Data Structure. Module 2, Array. Array is the simplest data structure where each data element can be randomly accessed by using its index number. For example, if we want to store the marks of a student in 6 subjects, then we don't need to define different variable for the marks in different subject. Instead of that, we can define an array which can store the marks in each subject at the contiguous memory locations. Arrays are defined as the collection of similar type of data items stored at contiguous memory locations. Arrays are the derived data type in C programming language which can store the primitive type of data such as integer, character, double, float, and other data types. Properties of the array. Each element is of the same type and carries a same size. For example, an integer is equivalent to 4 bytes. Elements of the array are stored at contiguous memory locations where the first element is stored at the smallest memory location. Elements of the array can be randomly accessed since we can calculate the address of each element of the array with the given base address and the size of data element. Need of using array. In computer programming, the most of the cases requires to store the large number of data of similar type. To store such amount of data, we need to define a large number of variables. It would be very difficult to remember names of all the variables while writing the programs. Instead of naming all the variables with a different name, it is better to define an array and store all the elements into it. So what are the advantages of using array? Array provides a single name for the group of variables of the same type. Therefore, it is easy to remember the name of all the elements of an array. Traversing an array is a very simple process. We just need to increment the base address of the array in order to visit each element one by one. Traversing a data structure means visiting or touching the elements of the structure and doing something with the data. Traversing is also sometimes called iterating over the data structure. Any element in the array can be directly accessed by using the index. Memory allocation of the array. All the data elements of an array are stored at contiguous locations in the main memory. The name of the array represents the base address or the address of first element in the main memory. Each element of the array is represented by a proper indexing. Two-dimensional array. 2D array can be defined as an array of arrays. The 2D array is organized as matrices which can be represented as the collection of rows and columns. 2D arrays are created to implement a relational database look-alike data structure. It provides ease of holding bulk of data at once, which can be passed to any number of functions wherever required. Stack. Stack is an ordered list in which insertion and deletion can be performed only at one end that is called top. Stack is a recursive data structure having pointer to its top element. Stacks are sometimes called last in first out or LIFO. The element which is inserted first in the stack will be deleted last from the stack. So applications of stack. We have recursion, expression evaluations and conversions, parsing, browsers, editors, and tree traversals. So operations on stack. A real-world stack allows operation at one end only. For example, we can place or remove a card or plate from the top of the stack only. Likewise, stack ADT allows all data operations at one end only. At any given time, we can only access the top element of a stack. This feature makes it LIFO data structure. LIFO stands for last in, first out. Here, the element which is placed or inserted or added last is accessed first. In stack terminology, insertion operation is called push operation and removal operation is called pop operation. Operations on stack. So we have the push. Push or pushing or storing an element on the stack. It is an adding an element into the stack. We also have the pop. Pop is removing an element from the stack, meaning to say we are going to remove or access an element from the stack. We also have the pick, tap, or stack tap. Look all the top element of stack without removing them. So we also have the pick, get the top element of the stack without removing it. We have is full, meaning check if stack is full. Is empty, meaning check if stack is empty. At all times, we maintain a pointer to the last pushed data on the stack, as this pointer always represents the top of the stack, hence named top. The top pointer provides top value of the stack without actually removing it. Linked list. Linked list can be defined as collection of objects called nodes that are randomly stored in the memory. A node contains two fields, that is, data stored at that particular address and the pointer which contains the address of the next node in the memory. The last node of the list contains pointer to the null. Uses of linked list. So we have the list is not required to be contiguously present in the memory. The node can reside anywhere in the memory and link together to make a list. This achieves optimized utilization of space. List size is limited to the memory size and doesn't need to be declared in advance. Empty node cannot be present in the linked list. We can store values of primitive types or objects in the singly linked list. Why use linked list over array? Till now, we were using array data structure to organize the group of elements that are to be stored individually in the memory. However, array has several advantages and disadvantages which must be known in order to decide the data structure which will be used throughout the program. Using linked list is useful because it allocates the memory dynamically. All the nodes of linked list are non-contiguously stored in the memory and linked together with the help of pointers. Sizing is no longer a problem since we do not need to define its size at the time of declaration. List grows as per the program's demand and limited to the available memory space. Sizing is no longer a problem since we do not need to define its size at the time of declaration. Array contains the following limitations. The size of array must be known in advance before using it in the program. Increasing the size of the array is a time-taking process. All the elements in the array need to be contiguously stored in the memory. It is almost impossible to expand the size of the array at runtime. Inserting any element in the array needs shifting of all its predecessors. Insertion. The insertion into a singly linked list can be performed at different positions. Insertion is adding an element at the beginning of the list. Based on the position of the new node being inserted, the insertion is categorized into the following categories. We have insertion at the beginning. It involves inserting any element at the front of the list. We just need to a few link adjustments to make the new node as the head of the list. Insertion at end of the list. It involves insertion at the last of the linked list. The new node can be inserted as the only node in the list, or it can be inserted as the last one. Different logics are implemented in each scenario. Insertion after specified node. It involves insertion after the specified node of the linked list. We need to skip the desired number of nodes in order to reach the node after which the new node will be inserted. Deletion and traversing. The deletion of a node from a singly linked list can be performed at different positions. Deletion deletes an element at the beginning of the list. Based on the position of the node being deleted, the operation is categorized into the following categories. Deletion at beginning. It involves deletion of a node from the beginning of the list. This is the simplest operation among all. It just needs a few adjustments in the node pointers. Deletion at the end of the list. It involves deleting the last node of the list. The list can either be empty or full. Different logic is implemented for the different scenarios. Deletion after specified node. It involves deleting the node after the specified node in the list. We need to skip the desired number of nodes to reach the node after which the node will be deleted. This requires traversing through the list. Traversing. In traversing, we simply visit each node of the list at least once in order to perform some specific operations on it. For example, printing data, part of each node present in the list. Searching. In searching, we match each element of the list with the given element. If the element is found on any of the location, then location of that element is returned, otherwise null is returned. Queue. A queue can be defined as an ordered list which enables insert operations to be performed at one end called rear and delete operations to be performed at another end called front. Queue is an abstract data structure somewhat similar to stacks. Unlike stacks, a queue is open at both its ends. One end is always used to insert data, or what we call in queue, and the other is used to remove data, or dequeue. Queue follows first in first out methodology. That is, the data item stored first will be accessed first. Queue operations may involve initializing or defining the queue, utilizing it, and then completely erasing it from the memory. Here, we shall try to understand the basic operations associated with queues. So we have here the enqueue, wherein we add or insert or store an item to the queue. Then, dequeue, meaning we need to delete or remove or access an item from the queue. Applications of queue. Queues are widely used as waiting lists for a single shared resource like printer, disk, or CPU. Queues are often in asynchronous transfer of data, where data is not being transferred at the same rate between two processes. For example, pipes, file I/O, and sockets. Queues are used as buffers in most of the applications like MP3 media player, CD player. Queue are used to maintain the playlist in media players in order to add and remove the songs from the playlist. And queues are used in operating systems for handling interrupts.